Let's look at OpenStax University Physics Volume 2, Chapter 13, Problem 36. Use Lenz's law to determine the direction of induced current in each case. So let's remember what Lenz's law says. Well, Lenz's law says that if there is a change in flux in a loop, then that loop will create an induced current so that the magnetic field created by that induced current will produce a magnetic flux that opposes the flux that induced the magnetic field. So it's a mouthful. Let's try to figure out how to apply this. So we know that in the first figure, we have a magnetic field that's out of the page. So I'm going to call this just B. Then as this beam is moved in, there are fewer magnetic field lines in this area, in the smaller area. So the magnetic flux decreased. So the magnetic field decreased. There are fewer magnetic field lines. So I'm going to say that the change in the magnetic field is in the opposite direction of the original magnetic field because it decreased. So decrease means opposite. Well, the loop itself then will induce a magnetic field to oppose the change. The change is that magnetic field into the loop. So an induced magnetic field in this direction will oppose the change, and that magnetic field was caused by a current that we have to figure out the direction of with a right-hand rule. We have to put our right hand inside the loop with our fingers sticking out. When we do that, we notice that our thumb can circulate around our hand in this direction. So it's going to go around in a counterclockwise direction. So the direction of the induced current is counterclockwise. Now, let's look at the second diagram, part B. So it is not drawn very clearly. To me, it looks like this coil, which here is round, is actually parallel to the magnetic field. So to me, it looks like while the magnetic field is in this direction, the area vector is in that direction, in which case the angle between the area vector and the magnetic field that comes out towards us is 90 degrees. So the loop will not be affected at all by the fact that it's pulled out of the magnetic field because there is no flux originally and there will be no flux afterwards either. So I'm going to say that the induced current is 0. Now in part C, we have a magnetic field originally in this direction. So this is B. And then as we're moving the loop more into the magnetic field, it picks up more magnetic field lines. So that means that the change in the magnetic field is also in this direction. So this is my delta B. Now the loop will want to induce a magnetic field to oppose the change by producing an induced magnetic field in the opposite direction of the change. And then when we're doing the right-hand rule, now we're going to put our hand inside the loop with our fingers into the loop. So our thumb will go around in this direction, and that's the induced current. So the induced current is clockwise. In part D, we have a magnetic field out of the board. So this is B original. And as we're pulling this beam out, we're increasing the area, we're increasing the magnetic flux, which means that there is going to be more magnetic field lines going out. So that's our delta B. Now the loop will want to induce a magnetic field to oppose that change. So that's the induced magnetic field. Again, it's opposing that change in the magnetic field. So now we place our right hand in the direction of the induced magnetic field. So that would be with our fingers into the loop. Our thumb is going to circle around in this direction. So this is I induced, and that will be clockwise. In part E, we have an original magnetic field in this direction. So this is our magnetic field. And we know that the magnetic field is increasing. So it will increase, it will get more magnetic field lines in this direction. That means that the loop will induce a magnetic field in the opposite direction. That would be this way. So these two are opposites. And that will be my B induced. Then to find the direction of the current, we place our right hand, the fingers coming out of the loop. So the hand has to be inside the loop, and the thumb will circle around in this direction. So this will be our I induced. And we have the current going clockwise. In part F, it looks very similar to part B, where I have an area in this direction, magnetic field is coming out, so the angle between the area vector and the magnetic field is 90 degrees. Let me just write this here. Area is perpendicular to the magnetic field, so there will be no induced current, so current is 0.